Chapter 12, alcohols and phenols. This time we are in the domain of the hydroxyl compounds. Okay, so out of the list of the functional groups that you guys have with you, you will find out that there is one, one particular group which is called hydroxyl group. That's the chemical group, but the functional group can be divided into alcohols and phenols. Okay, you would say that, well, I also can identify another hydroxyl group that is present in carboxylic acids. So why is it not included in this particular group, right, in chapter 12? Because carboxylic acid is a totally different functional group. So remember that carboxylic acids is really the combination of a carbonyl group, COO, and the hydroxyl. The combination of the two functional groups form a new functional group with totally different properties. Okay, so even though carboxylic acid, they also have hydroxy groups, but they are not part of the alcohols and phenols family. Okay, so the difference between alcohols and phenol, it will be basically the presence of an aliphatic chain or an aromatic chain. If there is a hydroxyl group next to an aliphatic chain or single bonded, that's what we call alcohols. If it's an aromatic ring or a benzene ring, we will call it a phenol. Okay, now I just wanted also to tell you how we are going to start doing this chapter from now on. Okay, so for example, in this particular chapter, we have alcohols and phenols. We will always do the same breakdown. Okay, so from now on, let's say like if we do all ketones and aldehydes, we will see common uses, common applications of the functional group, maybe a little bit of naming of the functional group. Not always, but in the most important cases, for example, for alcohols and phenols, we will do it now. Physical properties like maybe unusual boiling points, melting points, acidic properties, basic properties, a special resonance, maybe some electronic features that the function group has. Everything will fall under physical properties. Not all the function groups will have specific physical properties. Okay, synthesis. How do we synthesize alcohols? How do we synthesize phenols? And reactions of phenols and reaction of alcohols. Okay, so every single chapter that we are going to be doing, they will always include these sections. Okay, common uses, where we find them, and then naming physical properties, synthesis, and reactions. Okay, as I was mentioning before, well, alcohols and phenols, they are in the domain of the hydroxyl group. This one is the chemical group. The chemical group is called hydroxyl. Okay, the hydroxyl group is the one that is is the OH is the chemical group, but then the group is, the functional group is called alcohol. If it's aromatic, it will be called a phenol. What's the difference between alcohols and phenol? Well, for example, this one would be an alcohol, okay, and a phenol would be this one. Okay, so that's exactly what we were mentioning before. The term that we were using was aliphatic. This one is an aliphatic chain. What is an aliphatic chain? It's an open chain that has single bonds, right? So that's the aliphatic, right? So this one would be an aromatic chain. Well, not aromatic. So it would be an aromatic, compound. This one would be an aliphatic compound. So it's a chain. It's a chain, it's a continuous chain that is attached to a functional group. So that would be, what the term aliphatic, which is different from amphipathic. Amphipathic is right, AMPHIPATHIC. Amphipathic means that compound is acidic, is polar and non-polar at the same time. It's polar and non-polar at the same time. That's amphipathic. Amphoteric, which is what I would just make a amphoteric. Okay, amphoteric is the let me double check that The amphoteric compound, yeah, I was just making sure something. Amphoteric is the one that can behave as an acid and a base at the same time. Okay, so those are terms that are very important. They're going to be using a lot. Aliphatic means that it is just an open chain, saturated open chain. Aromatic is a benzene ring, right? We will learn later in the aromatic chapter that the aromatic compounds are not only benzene rings. Benzene ring is the best representative of aromatic compounds, but it's not the only one. Amphipathic is another term that means another definition that is really for defines what is a polar or non-polar compound. Okay, so for example, detergents are polar and non-polar. So we will call that amphipathic, right? And amphoteric are compounds that are, they can behave as an acid or as a base. Example, water, right? So we learned before that water can behave as an acid and also as a base. So that would be the definition for amphoteric. Okay, so those are terminologies that we will be using a lot: amphipathic, amphoteric, aliphatic, and aromatic. In the case of alcohols and phenols, well, we know that alcohol is an aliphatic compound. So the alcohol has an alkyl chain, an open chain, is aliphatic, saturated. Okay, does that mean that alcohols cannot have double bonds inside? Yeah, they can have double bonds inside. Are they still called aliphatic? Because of the property of being open chain, yes. So we will still call it aliphatic. Okay, so aliphatic is really like a general term that it has. It's something open, so it's like a linear, right? It's like a spaghetti, it's something like that. Okay, so that's what we call aliphatic. It's not only restricted to single bonds, right? So the aliphatic doesn't mean that it's only single bonded. It can also have double bonds and triple bonds inside as long as they are open chain, but they also have to contain single bonds. Okay, so and for phenols, they are aromatic. That property will give them different type of, that difference between aliphatic and aromatic chains, right? Aromatic groups, they will change, they will affect a lot of their physical properties. Okay, okay, good. So let's go back to these slides. Where do we find, well, why are they important? Why are we starting this chapter? I mean, this course with this first function group, alcohols. Alcohols are really very versatile compounds, meaning that from an alcohol, you can easily go to an alkyl halide. You can also get it converted into an ester, carboxylic acid, alkene, ketone, aldehydes, and ether. So it's a bridge. So in many of the syntheses that we are going to be learning later on, when we study carboxylic, esters, and aldehydes and ketones, you will see that alcohols will play a very important role. Why? Because they are like intermediates. If I want to make a ketone, I might want to do alcohols before, right? So if I want to make an alkene, I can do an elimination with sulfuric acid, I can get an alkene. If I want a carboxylic acid, I can easily do an oxidation. That's the principle how, for example, you guys make wine, right? Sorry, vinegar. Vinegar is made from wine, right? So how is that vinegar? Vinegar is carboxylic acid, it's acetic acid, and wine has ethanol. So if you oxidize ethanol, which is an alcohol, it will be oxidized to acetic acid, which is vinegar. Okay, esters the same way. So if you combine an alcohol with a carboxylic acid, you will get an ester, and then aldehydes just by partial oxidation, and ketone in the case of oxidation of a secondary alcohol. Okay, so right now you might not be familiar with all these terms that I'm just mentioning, I'm saying right now, but my message is like you guys are going to be learning alcohols, which is a very useful in the synthesis of higher order, right? Let's call it like that, order functional groups. Okay, so let's see, where do we find alcohol? So alcohol is right here. You guys can see, right, ethanol, cyclopentanol. This one is a cyclic compound, it's a cyclic alcohol. So we can find it in a lot of antibiotics. You can find it in the smells, right? You can find it in vitamins. Cholesterol has an alcohol. It's a cyclohexanol here. And then it comes in different variations, right? So sometimes they can be chiral, like in this case, and they will always have a specific application in biology, maybe also in chemistry for catalytic, catalyst, the active side of catalyst, they're very functional. Why are they like that? Well, they're like that because of the solubility, right? So alcohols, as we will discuss later, they are very good at forming hydrogen bonding. So they interact with a lot of polar substances and also non-polar substances. Why? Because the alcohol will always come with an aliphatic or another type of chain. For example, here, carbon chain. This region is very hydrophobic, or this part here. In geraniol, right? So in geraniol, you guys have this aliphatic region. So, for example, I would say that geraniol is an amphipathic, right? Amphipathic compound. Why? Because it has a polar head and also has a non-polar tail. Right? So, you would call this an amphoteric, right? So alcohols, they are very soluble in water, just the polar head, right? And depending how long it is, it can also be non-polar. If you are talking about ethanol, for example, ethanol is highly soluble in water. Why? Because the OH is very polar and the aliphatic chain is very small. It's very short. So it's not going to repel the water. Okay, so in the case of phenols are also used. This is phenol. That's the smallest phenol. If you have more substituents, of course, you will have a different phenol. Phenol is also used in a lot of biomolecules. Okay, so for example, here in capsaicin, right? In capsaicin is the spicy, right? The spice, the hot, right? The hot chili peppers. That type of feeling that you guys have in your tongue, or sometimes it swells, right? Your mouth. That's the capsaicin. Okay, so they are some researchers have been trying to explain, like how is the response of your body. Well, capsaicin is known for centuries that it is responsible for that spicy, right, hot flavor, right, of specific peppers. So you have another drugs, eugenol for thyme, right, from cloves. Sorry, from cloves. You guys have eugenol. It has an OH. They are all have pharmaceutical responses, biological responses. Okay, so phenols seems to be like a really good compound or really type of functional group that is appropriate for cell interaction, right? Because you see here is a poison ivy, right? Poison ivy, it is present in many plants, neurotransmitters, right? Here in cloves. Normally they say back home, they say that if you are chewing on cloves, right? Sometimes you can prevent some tooth ache, right? So if you have like some pain in your tooth, maybe your wisdom tooth or something, they tell you go and bite some cloves. The cloves will reduce the pain and the swelling, and in some cases it even can reduce infection. Okay, so that's what those are the properties of specific plants. In THC, I mean that's right? That's a tetrahydro cannabis, right? Cannabis, the extract of the cannabis, which is THC, right? So also has a property. So that's why I heard that there are some differences, right? Even in the cloves, right? The quality of cloves, or even cannabis, right? Or some other, the peppers depends on like the quality. That means that the phenol might be partially reactive, right? So if if it reacted already, so if it has been degraded, phenol, the disadvantage of phenol is that it is a very reactive compound. Okay, so it can survive for hours, but if it stays, so maybe it was exposed to the sun, it's exposed to specific chemicals, it might get degraded. So that's why the spices might be a little bit different. If you overcook something, maybe the spice will be different. It was not going to taste the same. Eugenol, for example, the cloves, right? So if you chew it for too long, I mean, you might be, or maybe you are eating something, maybe you're drinking soda, or you are drinking, let's say, milk, maybe the strength of the cloves is going to be decreasing, right? Why? Because you're supposed to chew on the cloves, just with an empty mouth to reduce the tooth, right? Sorry, the tooth pain, right? But if you're chewing it with something else while eating, it might affect it. You might lose the effect, right? So that's what I'm trying to say is that phenols are a very specific functional group. They're very useful in biomedical, biological, physiological applications, but phenols are very reactive. They can even get easily oxidized with air. So if they oxidize with air, they lose, right, those biomolecules right here, they lose their power. Is the same thing happening with alcohol? No, alcohols are less reactive. Okay, so you can leave alcohol outside maybe for 2 days, 3 days, but after that, yeah, it does react. So that's exactly what happens, right? With wine. Some people they say like, oh, that wine was like from yesterday or from 2 days ago. So that wine doesn't taste the same. True, it doesn't taste the same. Why? Because the alcohol gets oxidized, right? So the same as the phenol. The phenol also gets oxidized. So the taste will change a lot. So the ethanol, cyclopentanol, so it's not recommended for us to have cyclopentanol or ethanol, any alcohol really, exposed to the air for too long, because there is a reaction called oxidation, which is what we're going to be learning now later in this chapter. That's one of the most important reactions of alcohol. So any alcohol, please don't leave the container open. Okay, even the rubbing alcohol that we buy at the drugstore, uh, they don't last for that long. Okay, so this one, we're in the domain. Oh, I want to do a disclaimer. Phenol, even though phenol is a hydroxylic functional group, right? It's one of the two, alcohol and phenol, but the reactivity of phenol is so, I mean, it's so limited that we are going to be skipping the phenol part. All right, so we're going to be focusing mostly on the reactivity, reactions, and synthesis of alcohols. Maybe we will do some of naming and physical properties of phenol and alcohols together, but for the reactions and synthesis, we are going to be skipping phenol, right? All right, so let's go to physical properties and characteristics of alcohols. Right? So alcohols can be named depending on the branching, right? So you see here, that's what we call a primary alcohol. What's a primary alcohol? A primary alcohol is an OH, is an alcohol that is attached to a carbon. The carbon that is attached to the OH has only one branch, one carbon branch. That would be a primary carbon. This one is a secondary carbon. Why? Because the carbon that holds the OH, the hydroxyl, has two carbon chains. And tertiary alcohol is the alcohol uh, whose carbon, right, whose hydroxylic carbon has three carbon chains, right? It's three groups. So that would be primary, secondary, and tertiary. Right? So we already mentioned that alcohols can be amphipathic, right? Amphipathic molecules, because they have a hydrophobic region and a hydrophilic region, which is the green box, and the orange box is the hydrophobic region. They are very good at forming hydrogen bonding, right? So OH, right? The OH, delta minus, delta plus, they're highly soluble in water. They interact with other polar molecules because of the dipole moment that is present in the alcohol, in the OH group. The hydroxyl really is the key part. There are so many. DNA has a lot of OHs. Proteins, amino acids, they have OHs, some of them, for example, serine, threonine, tyrosine, for example, is a phenol. Some other amino acids, they have that type of polarity, but I think that for OHs, I think those are the only ones. Tyrosine, serine, threonine, those are the only three amino acids that have OHs. Sugars, they are all full of OHs. They are all polyhydroxylated compounds. So sugars, right? If we think of the three most predominant biopolymers that we have in our body, we have, lipids, DNA, proteins, carbohydrates, and DNA, right? In the case of lipids, yeah, no, lipids not that much. Few exceptions, but mostly we have in carbohydrate, proteins, and DNA, right? So what is this guy at the bottom? This guy at the bottom is called a wax. Okay, so let me open the. Okay, so this one is an alcohol, right? So this one will be an alcohol. So, but if that alcohol lets its chain grow, this one will be called a wax. What is the cutoff for wax? I would say 10 carbons or more. Yeah, 10 carbons. In this case, it's a little bit less. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, exactly 10. Okay, 10 carbons. So we will call this a wax. What is a wax? A wax is an alcohol with a long, aliphatic chain. At least 10 carbons. That would be a wax. This one is an alcohol. Is a wax a new functional group? No, wax is just a common name. It's a common name for an alcohol that has a greasy, we call it greasy, but it's really a non-polar, right? Non-polar tail. Okay? So it's a non-polar versus what we call the polar head. Professor, are waxes detergents? They could be. They don't use them, but there is a big difference between a wax. Okay, so I'm gonna tell you this one is a wax. And there is something that is totally different. Well, not totally, but yeah, this one. This one is a fatty acid. They are both lipids, right? Well, in this case, it's a lipid because it's very, very hydrophobic, right? Has a very hydrophobic chain, and this is also hydrophobic. So fatty acid, this is a detergent. If you deprotonate it, this one is a precursor for a detergent, the fatty acids. Okay, so what's the difference? I mean, yeah, they're present. I don't know, you guys, just to share, some knowledge. I don't know, you have noticed that sometimes you guys buy cleaning product for your stove, right? Or maybe for your, for your bathtub, right? Or your sink, or I mean, in general, any cleaning product that you want to get rid of some grease. Okay, and then you try the product and then you scrub, and then you remove some of it, but there is still a film that is not that good. So you say like, oh, this cleaner is not good, it doesn't get rid of everything, right? Or the commonly known as heavy duty, right? Heavy duty cleaners. Those heavy duty cleaners means that maybe they clean everything, waxes and fatty acids. Some other cleaners, no. Some other cleaners only get rid of the fatty acids, but not the waxes. Or some other cleaners they are good with waxes and no fatty acids. Okay, so why is that? What is that property? Why is it, if they look so similar, OHs, and why? Because the cleaners, sometimes they have a base. I don't know, you notice that some of the cleaners, they have ammonia. They have like a kind of like that strong smell, ammonia smell. The ammonia smell is a base. So as a base, of course, the base will only react with the fatty acid. The base is not going to react with the wax. So the base, that cleaner, that is ammonia base, of course, is only going to interact with the fatty acid. So if your grease, right, if the grease that you're trying to clean has waxes, the ammonia base is not going to clean the wax. It's only going to clean the fatty acids. So for example, that one would be perfect for kitchen, because in your kitchen, your stove, you will have most likely a lot of fatty acids. Waxes, no. Waxes are more for bathroom. Bathroom is part of the bathroom sink, the bathtub. Why? Because it's part of the grease that you release from your body, right? So it's the natural, natural kind of like moisture or waxes that you produce in your face. You use the soap. The soap will solubilize them partially, but then they get stuck on the walls of the bathtub, right? That type of film that has like a kind of like a grayish color, that's wax. Okay, so if you use this detergent or this cleaner that is ammonia based, you are not going to get rid of this. So you're gonna say like, oh, this cleaner is really bad. That's word. No, that is not bad. It's only that this is good for fatty acids. That's for kitchen or stove. There are some cleaners that are for both. Yeah, I know. There are some for both, but of course they're going to be more expensive, or maybe they're not going to be. They're gonna make that much foam. Sometimes we are always happier if we see a lot of foam, right? The foam will, you think like the foam will get rid of those scrubbles. It will clean it better. Not necessarily. I mean that foam is because you have detergent. To clean a wax, you don't need detergent. To clean a wax, right? So I mean, you need a different type, something more hydrophobic. So why? Because the fatty acid is attacked from two sides, from the hydrophobic side and from the polar side. Two targets. In the case of a wax, you can't. Why? Because in the case of the wax, this one is more predominant. The OH is polar, but it's not as polar as the carboxylic acid. And if you use an ammonia, of course, this one will be gone. You will have a carboxylate. It's going to be very polar. So carboxylate is way more polar because it's ionic, more polar than the waxes. So this one is going to be easier to clean. Fatty acids are easier to clean than waxes. Okay, so just to share, something about, cleaners and then, applications of the cleaners. Right. So tertiary, primary, secondary, tertiary, just a little bit to review. Okay. So for example, if I have this type of, right, this alcohol will be called secondary alcohol, right? Why? Because the carbon that is attached to the OH, right? This carbon has two carbons. Therefore, this one is secondary. Okay. What about this OH? This OH will also, right? So the carbon, this carbon that holds the OH has two carbon chains. Oh, professor, one is aromatic. That doesn't matter as long as it's carbon. Carbon, carbon, secondary. Okay. Um, Terbutanol. Terbutanol, the carbon that is attached to the OH, right, has three carbon chains. Tertiary alcohol. Okay, now here in the slides, we don't have the naming, but I'll just briefly show you the naming. You might find it in some of the homework problems. I'm not going to be asking specifically in the quizzes and exam, but you might see it later on in some other tests. For example, if you guys are going to medical school, going to the grad school, GRE, MCAT, PCAT, the DAT, all those you definitely you might see some naming. So the ending for alcohol is all. Okay, so if this guy used to be called 1, 2, 3, 4, you used to call it butane, right? Butane, because it has 4. Now it's going to be called butanol. And of course, you have to indicate the location of the alcohol. In this case, the alcohol will be on carbon number 1. 1-butanol. What about this guy? Well, 1, 2, 3, 4, 5. It doesn't matter where I start counting. It's the same distance from the OH. 1, 2, 3, 1, 2, 3. So I can start counting here. 1, 2, 3, 4, 5. So I will call this 3-pentanol. Okay? Pentanol, because it's 5 carbons. This one. Okay, so of course it's a ring. The ring starts the numbering on the carbon that has the OH or the highest number of substituents. 1, 2, 3, 4, 5. So it will be 1-methyl, 1-cyclopentanol. Cyclopentanol. Okay, the substituent is the methyl, so that's why I go like 1-methyl, 1-cyclopentanol. The cyclopentanol, well, here cyclo is 5 carbon, right? It's 5 carbon ring, and then the 5 carbon ring has, well, the cyclo prefix because it's a ring, and then pentanol, ol, is because of the functional group, right? Which is the OH. All right. Another one, let's see, something simple like this. I mean, we're really not going to do that much in terms of naming. So let's say, what if I have two alcohols? Okay, you have two alcohols. Well, you start numbering the longest continuous chain again. It will be either right or left. In my case, I will give priority to the right. Why? Because it's closer to the substituent, right? So in this case, it will be a diol because it's two alcohols. So it would be 2,3 heptane diol. Okay, heptane. Why heptane? Because it has seven carbons. Diol, because it's two diols, 2,3, and then I have to indicate the number where they are located, 2,3. Professor, but they are chiral. Should I also include the RS? Yes, technically you have to include the RS. Yes. 2 whatever, comma 3 whatever, right? So I'm not gonna do the chiral, the chiral analysis, the RNS, but yeah, you should include what is the chirality of carbon number 2, what is the chirality of carbon number 3. Yes, that will be the official number, right? Official name for this compound. Once again, do we need to study for the quiz or the exam? No, I'm not gonna. But I'm relying on you guys that whenever I tell you pentanol, or if I tell you cyclobutanol, You know, guys know what I'm talking about, right? Cyclobutanol. Butanol is cyclobutane, and cyclobutanol means that it has an OH, right? If I tell you 2-methyl, 1-hexanol. Okay, how do I do that? Well, do first the backbone hexane, right, or hexane. 1, 1, 2, 3, 4, 5, 6, right? That's my backbone hexane. And in carbon number 1, I have the ol, the OH, and in carbon number 2, I have the methyl. That's it. Okay, so you do by pieces, but first you have to draw the backbone. In this case, the backbone is hexanol, hexane, right? So hexane will be my main the backbone on this scaffold, right? For this compound. Okay, so once again, don't worry about the that much about the naming for in case of for our test, but at least we know, right, how these guys alcohols are named. Okay, let's continue with the physical properties. In the case of the physical properties, the next one is acid-base properties. Alcohols, even though alcohols they are not like that acidic, but we know that oxygen is a electronegative group. So electronegative groups they have a dipole moment. So you have an OH, definitely it's going to have a delta plus and a delta minus. So that delta plus delta minus will create the opportunity for a strong base to deprotonate it. Right? So in the case ethanol with sodium hydride, right, it will produce sodium methoxide and hydrogen gas. Ethanol with sodium metal, you can also use sodium metal, it will produce the same sodium methoxide and hydrogen. Okay, this one is sodium hydride. Cyclohexanol also will also get deprotonated because those are alcohols. Okay, so let's see, let me just go over this because it's very important to understand. Okay, so the efficiency of using sodium hydroxide, you say like, Professor, why sodium hydride? Can I use sodium hydroxide? You will still get some, okay? You can still get some deprotonation, but in really low yield, very low yield. Why? Because sodium hydroxide is not strong enough to remove that hydrogen. The pKa of alcohol is about 16. If you don't remember what pKa is, please just go back to organic one. So we need to know, we need guys to remember what is pKa and what is considered a weak pKa or a strong pKa, right? A strong acid or a weak acid. Go to chapter 3 in organic chemistry 1, acid and bases, and get an idea what means a stronger acid, a weaker acid, and super weak acid, right? So we need you guys to catch up on that because it's a prerequisite for this class, right? So pKa of 16, so it's a weakish, right? Weakish acid. So if a weakish acid needs a stronger base to eliminate it, the pKa, I mean this base is not that strong, so it will deprotonate it, but in a very small yield. Some people, they even use potassium hydroxide. Potassium hydroxide is slightly more basic, so you will have maybe a slightly higher yield. But if you want a more efficient deprotonation, I would say that you guys have to use either sodium hydride or sodium, plain sodium. Okay, so it will produce O minus here and also O minus here. Okay. Oh, what happened with the sodium? What happened with the sodium here? Remember, once again, they are spectator ions. They are not going to be part of the product. You can put them as Na plus at the very end, but please don't do any attachment here like I have seen in the past, or even some people, they put 2 sodiums there. No. There is no presence of sodium in the scaffold. There is no carbon sodium bonds at all. Okay, so they are spectator ions, so ignore the sodium. Like, so the only thing it's gonna be doing is a deprotonation. And then how does that happen? Okay, so it happens like this. OH, you wanna know the mechanism, right? We don't need to know this mechanism, but the H, right? The H minus attacks the hydrogen and the oxygen takes the electrons. So the result would be minus and then H, right? Which is H gas. That's why you get H2, which is yeah, hydrogen gas, right? So you got the ethoxide. So here would be propoxide. Okay. So when you have propanol, 1, 2, 3, yeah, propanol. So propanol deprotonated would be propoxide. Okay, that's the proton. The conjugate base is called propoxide. So you can do it with hydride. This one is the hydride anion. Very strong base. Okay, good. Let's continue. Oh, about the other case. So they were comparing about the acidity, right? So for example, they had cyclohexanol. They were trying to explain why is it that phenols have a pKa of about 10, and the cyclohexanol has a pKa of about 18. Right? I think it was 18 on this slide. Okay? So explain why hexanol, cyclohexanol, and phenol, they have this difference in pKa, even though they only, right? The structure is very similar, except the double bond. Okay. So the reason is very simple: resonance, right? So in the case of phenol, you guys deprotonate the phenol, right? The phenol gets deprotonated with a base, and you guys will get O minus. That could be the conjugate base. This conjugate base is stabilized by resonance. Once again, if you guys don't remember resonance or how to draw resonance structures, go back to Organic Chemistry 1 and study Chapter 2. Chapter 2 resonance goes really deep into resonance stabilization. So OH, the conjugate base, is highly stabilized. The conjugate base is stabilized by resonance. So what, right? That's the big question. So resonance, if your conjugate base is stabilized by resonance, the pKa will decrease, meaning that it will become more acidic. Because if the conjugate base is more stable, that means that the reverse reaction is going to be less favored. Since this one is more, remember, nature always goes to the most stable form. If the right side is more stable, then the arrow will be more, right? It will go more to the more stable. It won't go back that much. Okay? So that means that it's more acidic. In the case of this cyclohexanol, if you deprotonate it, this is going to be your conjugate base. But if you see, this conjugate base has no resonance stabilization, there is no conjugation here I can use to delocalize that minus charge. Here, the minus charge is efficiently delocalized, right? Using this conjugation, lone pair, single, double, single, double, single, double, single. It will move around. So the negative charge is not going to be fixed in the oxygen. It will get delocalized. It will be dispersed in the entire molecule by resonance. That's good, because we need the charge to be delocalized. The more delocalized the charge, the more stable the compound will be, right? So that's why the resonance will make it more stable. So why are phenols more acidic? Phenols are more acidic because they are the conjugate base upon deprotonation, right? It's more stabilized by resonance. If it's stabilized by resonance, it's more stable. If it's more stable, it makes it more acidic. If it's more acidic, the pKa will be lower. Okay. In the case of cyclohexanol with no resonance, you can still deprotonate it, but there is no stabilization by resonance. So there is no, the pKa will remain its conventional value, right? You see, cyclohexanol has a pKa of 18 and phenol has a pKa of 10. So you would say, like, Professor, why here for phenols you are using sodium hydroxide? Yes, because since a phenol is a stronger acid, stronger than alcohols, then it needs a weaker base. It can use a weaker base. But Professor, can I also use sodium and sodium hydride for phenol? Absolutely yes. You can use sodium and sodium hydride also for phenol. This strength is not needed, but you can still use it. But it would be more appropriate to use sodium hydroxide. Can I use sodium hydroxide for ethanol or cyclohexanol? Yes, you can still use it, but remember that the yield, the amount of the protonation you will get, it will be very, very small. You can still do it, it will deprotonate it, but in very small percentage. Okay, so this one summarizes the resonance stabilization. You guys will, this structure will bring back memories from organic chemistry 1. You deprotonate the oxygen, gets O minus, delocalization once, delocalization twice, third time, fourth time, and then that's the final structure, right? So you guys have at least 4 resonance structures. That's how the molecule gets stabilized, right? Good. So that's the acid and base properties for alcohols and phenols. That explains why alcohols are less acidic than phenols. Another type is, I mean, we recall from chapter 3 about acid and bases. There's also called ario, right? So whenever you guys have an alcohol with halogens, these halogens will produce an induction effect in the alcohol. So if an alcohol, this one is ethanol, right? More or less ethanol. So ethanol has, let's say, a pK of 16. The presence of chlorine by induction, it will bring down the acidity. Why? Because these guys are electronegative. If they're electronegative, they will pull electrons, and then they will decrease they will increase the polarity of the OH by induction. So if the OH bond is more polar, that means that the compound will be more acidic. What about terbutanol? Why is terbutanol less acidic, right? Remember, the higher the pKa, the less acidic the compound is. So in the case of terbutanol, why is terbutanol less acidic? Because terbutanol has a steric hindrance, right? So bulky, methyl, 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 3 bulky groups, right? Or at least they are not that big, but there are 3 of them. It's a tertiary alcohols. Tertiary alcohols are less acidic. Why are they less acidic? Because they prevent the interaction of the solvent. So the solvent does not interact as efficiently with the conjugate base. Okay, so maybe that would be better to explain it by hand. Okay, so for example, if you guys have a propanol right here, if you deprotonate it, right? Remember, you deprotonate it, you produce the conjugate base. So this conjugate base is ionic. So how do you stabilize an ion? With solvent. The solvent will stabilize it. Solvent. Okay. What happens if instead of that I have a terbutanol? Okay. So you will deprotonate it. So you have also to stabilize it with the solvent. But since this compound is so bulky, right, has a lot of branches, then the solvent is going to have a hard time. The solvent will not efficiently hydrate, right, or solvate. We call that solvate. Solvate the ion. This O minus needs to be solvated. So since there are so many branches, right, so many carbon chains here, so carbon groups, in this case is methyl, but it can go worse. So you have so many carbon groups here, it will prevent the solvent from interacting. So this one is going to be less stable. This one will be more stable. What happens when something is more stable? Well, if it's more stable, the equilibrium will be shifted to this side. Less to this side. This one is less stable. That means that this one will be favored, the opposite. Remember, this is more stable than this, so this is less stable, so the reaction will run away from that less stable form. So if it's more stable this way, the pKa will decrease, making it more acidic. If this is less stable, the pKa will go up, making it less acidic. Okay? That's explanation of why tertiary alcohols, right? Or yeah, it doesn't have to be tertiary, but any bulky, right? Because sometimes you can have a secondary alcohol that it has 2 rings, let's say. Yeah, of course they're gonna be less stable, right? They're gonna be bulky. Okay, let's keep going. That's the resonance, right? Resonance stabilizes, that's part of the ario. Remember ario. I'm just going to be brushing up a little bit on ario, right? Remember, it's the atom, resonance, induction, and orbital. In this case, the resonance effect, the R, is really what plays a role here. So why is compound A more acidic than compound B? Well, it's because of the resonance. See, the oxygen and the oxygen is conjugated to the double bond. So that makes it more stabilized by resonance when it becomes the conjugate base. Okay, good. So we finished so far the physical properties of alcohols. There is no more to talk about. Now let's go over the synthesis. How do we make alcohols, right? Have we made alcohols in the past? Yes, we have made alcohols in the past. These reactions are not new. You guys studied those already. So this one. So you made alcohols from SN2 reactions, from SN1 reaction. So for example, you had a primary alkyl halide with sodium hydroxide. The sodium hydroxide will do a backside attack to the substrate, and the leaving group, in this case chloride, will leave. So you get a primary alcohol. Tertiary alcohols with an SN1, you use a weak nucleophile like water. So water will attack, no, it will not attack. First, you have the dissociation of the substrate. You form the carbocation. In this case, there is no need for carbocation arrangement. So the carbocation will be attacked by the weak nucleophile, which is in this case is water. So you guys can make alcohols, either primary or tertiary, from SN2 or SN1 reaction, respectively. Okay. Remember, sodium is not needed, HCl is not needed. So if you you guys have to write a product for a reaction, you can only focus on the carbon base, right? The organic compound. So this is inorganic, so you don't really have to state it. Alternative ways to make alcohols we have from alkenes. Alkenes can be converted into alcohols. How? With a reaction called hydration. Hydration reactions can be used to produce alcohols, right? So for example, you have an alkene, I can use dilute sulfuric acid and will give me the alcohol, Markovnikov, or the oxymercuration. Oxymercuration, mercury acetate in water, followed by sodium borohydride. That's also Markovnikov. What's the difference between these two? The oxymercuration will not give room opportunity to carbocation arrangement. The acidic acid catalyzed hydration, it does produce rearranged products if, right, if rearrangement is potential, right? In this case, it's not potential because you're getting a secondary carbocation, so definitely you guys will not have rearrangement. But if there is opportunity for arrangement, the acid catalyzed will do it. And the last one, the third reaction is hydroboration. Hydroboration, borane in THF, followed by hydrogen peroxide and hydroxide. It will add the OH to the least substituted. That's called the Markovnikov addition. Sorry, anti-Markovnikov addition to the alkene. So in the alkene, you guys will have two ends, right? The most substituted or the least substituted. If it's Markovnikov, it will add to the most substituted. If it's anti-Markovnikov, it will add to the least substituted. What if they have the same branching, right? So let's say like secondary, secondary, or one branch, one branch. So if you have the same number of branches on each side, then the Markovnikov will be both. You will have one alcohol here, one alcohol here, right? So maybe I'll just explain it with an example. Okay, so let's say like what to do, right? If I have, yeah, okay, this particular alkene, what if I do oxymercuration? Mercury acetate, water, sodium borohydride, right? Uh, I have to decide which one is my Markovnikov side. This one is my Markovnikov. This reaction is Markovnikov. So we'll add OH here. So my product would be OH, no CCR. Why? Because this reaction doesn't give room to CCR. What about if I have now this compound? If I do Markovnikov, sorry, oxymercuration, Markovnikov. Now I have to decide which one is my Markovnikov and anti-Markovnikov side. In this case, this carbon has two branches. This carbon has two branches. So there is no difference. Oh, but this one is an ethyl. Does that make a difference? No. What makes a difference is the number of branches. So you will have an alcohol here and also an alcohol here. Why? Because both of them are Markovnikov. So you should report two alcohols. This one and this one. Two alcohols. One here and one here. Why? Because there is no Markovnikov here. Both of them are Markovnikov. Professor, can we also tell that both of them are anti-Markovnikov? Yes. You can also tell that both of them are anti-Markovnikov. There is no difference. So you will do OH here and OH here. Professor, this carbon is chiral. Should I declare it? Should I state it? Yes, you can do that. It will be here, since this is chiral, right? This one plus an enantiomer. Okay, you really have two products here because it is a chiral. It's a chiral center. This one is not chiral. Oh, actually it is chiral. So you guys will have here, this one is chiral plus an enantiomer. Yeah, right? Because this is a chiral center. So you will get actually four products here, right? This one with its enantiomer pair, and this one with its enantiomer pair, because this is a chiral center and chiral center, right? You will produce both products. Okay, so this is just an exception, right? In which you see that an alkene has the same branching, two branches, two branches. So I can distinguish Markovnikov, anti-Markovnikov. Same thing applies to hydroboration. Right? In this case, if I am doing hydroboration, BH3THF, sodium hydroxide, hydrogen peroxide. I spend more time writing than explaining. Here, this one is an anti-Markovnikov. So here, one branch, one branch. They both have the same number of branches. I cannot distinguish which one is my my anti-Markovnikov. Then I will have two products, one here and one here. So my two products will be OH. This one is not chiral, and the other one is, yeah, okay. One here, that's this one, and one here, that would be this one. But this one can go wedge or dash. That's why you guys produce OH with enantiomer. So you should technically be producing three compounds. Do I need to draw the enantiomer structure? Do I need to draw the, right, with the dash? No, no, you don't need to draw with the dash. So just by writing enantiomer or stereoisomer, that's okay. Okay, you don't need to draw all three. You can just write the two, and that one that has enantiomer, just next to it, just write plus enantiomer. So I know that you're really aware of the chirality of the compound. Okay, let's continue. So those are reactions that we already studied. You should already be, familiar with those from organic chemistry 1. So let's continue. New reaction. These are actually new reactions that you guys are going to be studying in this chapter. So they are going to be reductions. So you can make alcohols also from aldehydes, from carbonyl compounds. Carbonyl compounds, they can be aldehydes, ketones, carboxylic acid, and esters. Okay, so there are two reduction reagents, sodium borohydride and lithium aluminum hydride. Lithium aluminum hydride can be abbreviated as LAH. Sodium borohydride unfortunately doesn't have an abbreviation. You guys have to spell it completely. Sodium borohydride. Sodium borohydride. That one is longer. You will find longer names, to be honest. Later on, I will tell you, something that is very funny things that happened to me when I went to the nutritionist once. I'll tell you once we study a longer name. Yeah, it's a very fun experience. All right, so carbonyl containing compounds, right? So you guys have ketones. This is a ketone, can be an aldehyde, carboxylic acid, or esters. They can be reduced to alcohols by using sodium borohydride or lithium aluminum hydride, LAH. This one is another reaction you can also use, but that's only for, I think this can also be used for aldehydes and ketones. But I would say do not use this one. It is possible you won't get penalized from if you use this one. But the disadvantage of H2PD or H2PT is that this reaction is also used for alkenes and alkynes, right? So it might have a lot of, like side products or undesired compounds or undesired products. So I would say avoid it. Unless you have a very plain ketone or aldehyde, then I would use this one. But if not, please just try to avoid that. We're using these two new reagents, so there is no need for you guys to memorize a third one. So just use these two. Okay, so I think the best is to do it by hand. Okay, so synthesis. Now let's make new reaction. Synthesis of alcohols. Okay, reduction of carbonyls. Okay, so I just want to tell you something about, organic compounds in general, which is the oxidation trend. Okay, so how do I know that a compound is more oxidized? Right, so like at least for metals in inorganic chemistry, that's easier, because if you say like zinc, right, zinc 0, zinc plus 2, the charge goes up. I know that it's more oxidized, right? Or in the case of lead, lead 0, lead plus 2, lead plus 4, right? I know that this one is more oxidized than this, and this is more oxidized than this. At least for the oxidation state, I can tell how is the oxidation of the metal. But we don't have that in organic chemistry. We don't work with charges. Why? Because all carbons, right, they have covalent bonds. They don't form ionic bonds. So how do I know? So it goes by the number of bonds with oxygen, or also the number of bonds with hydrogen. Okay. So you tell me, for example, methanol. How many bonds is methanol, right, having? How many COs is methanol having? Methanol has one bond, one of them. What about acetaldehyde? Has two bonds, C double O, right? One and one. What about formic acid? Formic acid has three bonds with oxygen, one, two, three. So this is the oxidation trend. Alcohol is less oxidized than aldehydes, and aldehydes are less oxidized than carboxylic acids. Okay, so that's the oxidation trend. Oh, Professor, what if I have methane? Yeah, of course, this one has zero bonds. Yeah, that one will be the least oxidized, right? It has no. And then at the same time, you can see that the number of CHs changed, right? This one, how many CHs? Four. This one, how many CHs? One, two, three, three. This one, how many CHs? Two. This one, how many CHs? One. See, when an organic compound gets oxidized, the number of CO bonds increases, and at the same time, the number of CHs, right, CH bonds decreases. Oh, can it happen the case in which, you know, the number of hydrogens or oxygens change, but not at the same time, meaning that I change the number of carbons, sorry, the COs, but I don't necessarily change the number of hydrogens. Yeah, that's true. You can also have that. So the number of, you know, one of the two has to change. That's what I'm trying to say, right? So either the number of COs increase or the number of CHs decrease, or both, right? But one of those two events, at least one of those two events has to occur. Both of them sometimes occur, but not necessarily. So you see here, then alcohols are in the reaction path, right? Oxidation path, right? For organic compounds, right? When they get oxidized. So that means that alcohols can be created, how? By reducing, if I reduce, right? This is the oxidation route. That means that this is the reduction route, right? This one is the oxidation, this one is the reduction. So how can I make alcohols? I can make alcohols by reducing aldehydes or by reducing carboxylic acid. I can go all the way to alcohols. And that's what we're going to be doing now. So we will oxidize, sorry, reduce, right? So you guys have a ketone. If you reduce ketones with sodium borohydride, followed by acid, right? This C double O will get reduced to alcohol. See, this double bond gets reduced to OH. What about if I have an aldehyde? Can I have an aldehyde? Yes, you can also have an aldehyde. Aldehyde, sodium borohydride, H3O plus. That one gets reduced to alcohol. Okay? You see, this carbon is reducing the group to a primary alcohol. So something very important for you guys to see. How do I make primary alcohols? From aldehyde. How do I make secondary alcohols? From ketones. Okay, so that's something that you guys have to analyze. Like, oh, I want to make a secondary alcohol. Okay, so you're gonna make a secondary alcohol, then reduce a ketone. I want to make a primary alcohol, then reduce an aldehyde. Oh, what about, Professor, if I want to do tertiary alcohols? No, tertiary alcohols are made in a different way. You cannot make tertiary alcohols from reduction. Okay. Okay, Professor, what happened with LAH? Okay, so that is coming next. Sodium borohydride is a mild reducing agent. Okay, so you saw it on this slide, right? You had sodium borohydride and you also had LAH. So you had two reducing agents. Sodium borohydride is a mild reducing agent, and that's really what we use for ketones and aldehydes. You can use both. I mean, for both the species, for those compounds, for those functional groups, you use sodium borohydride. Lithium aluminum hydride is used for higher, more oxidized species. Why? Because sodium borohydride is so weak that it's not reducing enough to react with carboxylic acid or esters. Okay? If you see esters and carboxylic acid, they are more oxidized. Let's say propionic acid. You have propionic acid. This one has is more oxidized. 3 COs. This one is only 2 COs. So sodium borohydride is enough to reduce it. Sodium borohydride is enough to reduce it. But sodium borohydride will not reduce carboxylic acid. This is too oxidized. Sodium borohydride is too weak, so you will have to use LAH. Okay? Also acid. So what happens? 1, 2, 3, and 3 will have the OH. Okay? 1, 2, 3, 1, 2, 3, OH. You get rid of the carboxylic group. It got reduced. See, from 3 oxygen bonds, now you have only 1 oxygen bond. It gets reduced. Oh, do I have to say excess 2 moles or something? No. Just write LAH. That's enough. If you want to write the excess, yeah, that's fine. But you don't really have to. Okay. So what is the other compound? Esters. Esters can also do it. If you reduce an ester, you actually get 2 alcohols. Okay. Why? Because the ester will get broken in the middle. So you will have 1, 2, 3, 4 OH. 1, 2, 3, 4. 1, 2, 3, 4 OH. And what happened to the other half? The other half will also have OH. 1, 2, 1, 2. So in the case of ester, you split it, and then each side of each half, right, we have an alcohol. Alcohol here, alcohol here. So 1, 2, 3, 4, 1, 2, 3, 4, OH. 1, 2, OH. 1, 2, OH. Okay. Professor, can I use sodium borohydride here? No, you cannot use sodium borohydride. If you use sodium borohydride, it will give you no reaction. Here, the same thing. If you use sodium borohydride, it will give no reaction because it's not strong enough. You need something stronger. Lithium aluminum hydride is a stronger reducing agent. Professor, can I use LAH here? Yes, LAH, you can use it here. Sodium borohydride or LAH give you this. Sodium borohydride or LAH, they give you this. Oh, Professor, the same thing. So here you produce secondary alcohol from ketone. What about for carboxylic acid? Carboxylic acid will always give you primary alcohols. And esters will always give you primary alcohols as well. You see it here. Okay, so some practice problems. Let's see. Right, let's see to practice some reactions. Sodium borohydride. Oh, we will do the mechanism in a second. Okay, so these 3 reactions. Okay, I have a ketone here. Ketone with sodium borohydride, it does get reduced. It works. So the skeleton is preserved. You don't really lose a skeleton. The skeleton will be the same. Only this part will be shift to an OH. In this case, it's chiral. So I would say the alcohol would be formed there. It doesn't move. There is no CCR. And then, of course, plus the enantiomer. Because the alcohol that I'm forming is chiral. Or what about this one? This is also chiral. Yeah, this is also chiral, right? But if they don't specify in the reagent the chirality, in the product, you can also leave it alone. You don't have to say it. But yeah, technically, yeah, it should give you, it will be the same. So if this one is wedge, this one will be wedge. Yeah, okay. Here, ketone again, okay. Nothing changed except this. Is this chiral? Yeah, actually it is chiral. It is chiral, right? Because here, this side is different from this side. I have a hydrogen, it's 4 different groups. So it will be that plus enantiomer. So in this case, you do get two products. LH is okay, but Professor, LH is strong. Yeah, it's strong, but LAH reacts with everything. That's the advantage of LAH. It can work with anything. In practice, no, it's more difficult to use LAH. You need like a special box. You need to be very careful with lithium aluminum hydride because it's very reactive. It can even react with the moisture of the air. You need like a special, what we call in organic chemistry, glove box. It's a box that has two holes where you just work inside with your gloves. No air goes inside. It's like you flush it with nitrogen. You displace the air with nitrogen. So inside it is only nitrogen gas. There is nothing else. So there is no way how the lithium aluminum hydride can, get decomposed or can do like any side reaction. Okay. And then the last one, we have a carboxylic acid. I'm using LAH. It works. So I should get a primary alcohol. Okay. 1, 2, 3, 4, 1, 2, 3, 4, OH. Okay. Okay, great. So those are examples, good examples here, right? Aldehyde, sodium borohydride or lithium aluminum hydride for primary, ketones, sodium borohydride or lithium aluminum hydride, secondary alcohol, carboxylic and esters, primary alcohol, and you use LAH only. Don't try to use the other compound. Okay. Great. So now this is the mechanism. So the mechanism, yeah, I would do it by hand, but it's just a repetition of what you have in here. I will do it, but that's really a summary of the both reductions. So this one is the reduction with LAH, and this is the reduction with sodium borohydride. This one is the mechanism for the reduction of the ester, for example, okay, with LAH. Okay, so it attacks, they're all, if you learn one, you will know the other two. So there are just few adjustments for the other species. Okay, so let's do it. I'll just do one for each. Okay. Mechanism. Do we need to know this mechanism? Yes, that's why I'm doing it. Okay, so reduction of what? Let's do 2-butanone. 2-butanone with sodium borohydride in acid. Now you guys will understand why acid. The product would be 2-butanol. All right, so let's do it. Sodium borohydride, the Lewis structure sodium borohydride is BH4 minus. Remember, the sodium is always a spectator ion. So the BH is the active. So the H will it will not migrate. It will attack this bond. Will attack the C double O. And since this carbon already passes the octet, it will push the electrons towards the oxygen. What happens next? Okay, the oxygen got displaced, or minus. This H got added here. What happened with the boron? Well, the BH3 just leaves neutral. Right? That's a side product. BH3. Okay, that one. Okay, next is very easy. Next is just the H3O plus. Protonation. So the oxygen, right? oxygen gets protonated, it's a proton transfer here, gets protonated, and the oxygen takes those electrons. Be very careful about the mechanism. Look at how I'm doing the mechanism. So that's also what we're expecting to see in the quizzes and the exams, is there is a meaning, this one. Some people, they do it H, no. Boron, no. The minus, no. What is attacking? This BH bond attacks this carbon, and at the same time it displaces the double bond towards the oxygen. You get that now that, well, if you want, you can do this lone pairs, yeah. So the lone pairs, now you get a third lone pair, the hydrogen gets added, the BH3 leaves, right? Or is on the side, then the oxygen with the minus, the lone pair attacks the hydrogen, not the minus, not the O. It's the lone pair of the oxygen, the one that attacks the hydrogen, and then this bond that it was attached to the H3O plus or the water, it will get returned to the water, right? To the oxygen. Okay, be very mindful. Don't forget the charges, charge here, charge here, charge here. So, and then after that, well, the product will be OH, 2 lone pairs, and water. That's it. That's your product. That's the end of the mechanism, right? Not difficult at all. Is LAH the same? Very similar. LAH will be very similar. Let's use propanol. They tell me with LAH to, let's do it with water this time, because it can also be done with water. You will get propanol. Okay. Okay, so let's start the mechanism. LAH. LAH, lithium aluminum hydride, aluminum. This is the structure of lithium aluminum hydride, very similar to BH4. Remember BH4, right? Same thing. What happened with the lithium? The lithium will be a spectator ion on the side. It does not participate. Next is the attack, very similar attack. The HAL, the bond goes towards the oxygen, sorry, carbon. The carbon pushes, right, the double bond towards the oxygen. The aluminum, right, with the 3H's goes to the side, does not participate anymore. Doesn't have a charge because the charge was really associated with the H, the extra H that it had. But since now the H went with the aldehyde, then this one gets neutrality. So what happens with the aldehyde? The aldehyde now gets the hydrogen added, right, to this carbon, to the side, and then the oxygen gets negatively charged. Then the next step is the addition of water. No H3O plus. You have to look what you have here. In this case, they're telling me add water. Then I have to use water. Is it wrong if I use H3O plus? Yes, of course it's wrong because you're not giving H3O plus, you're giving water. So next will be the attack, this one, and then this one attacks, goes back to the oxygen. Okay. Dun, 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 dun. OH plus OH minus. And that's your product. Propanol. Okay. 1, 2, 3, OH. 1, 2, 3, OH. Propanol. Okay. Now, the last mechanism, that's with the carboxylic, the ester, right? Ester with LAH. That ester with LAH. Let's use, yeah, let's do a, you guys have the ester, right? On the slide. Let's do a lactone. What is a lactone? A lactone is a cyclic ester. It's a common name. Okay, lactone. It's an ester that is in a ring. Okay, so lactones can also undergo reaction with LAH. Of course, absolutely, they do. Right, so the reaction is with LAH. First step. Second step is acid. Let's do this one with acid. H3O plus. Okay, so let's do it. First is the LAH. H minus lithium on the side, spectator. So same strategy. The H bond, right? This bond attacks the carbon. This carbon breaks the octet, right? If it takes those electrons, so that's why it pushes to the oxygen. Next could be, right? This H, it's added, right? This H in red is added to the carbon. 1, 2, 3, 4. Okay, we're good with the octet. Next is that this O minus is too unstable because it has a charge. So what it will do, it will go back down to reform the double bond. I will push this towards the oxygen. Professor, why towards the oxygen? Why not towards the carbon? No, because oxygen is more electronegative. If therefore, if somebody has to take electrons, of course, the one that's going to take the electrons is going to be the most electronegative. You will not give it to the carbon. You will not give it to the hydrogen. It has to go to the most electronegative. It will be the oxygen. If I have a Cl here, let's say, right? If I have a Cl, then the Cl will take the electrons because it's more electronegative. If you have a fluorine, then it would be the fluorine because it's more electronegative, right? So in this case, comes back down. I made a mistake. Okay, so this one has double O, right? It comes back down. The H will go to the side, and this one, right? The oxygen minus. Who is this oxygen? Let me get it in yeah, this oxygen is this oxygen, right? It opened, basically it opened. I broke the lactone. The lactone opened up. It broke, right? Split. So that's why the oxygen comes down here. So who is this carbon? This carbon is right here. I just moved the hydrogen, right? It used to be the hydrogen on the left. I just move it to the right to make it more visible. Okay, good. Next is that we have excess. Let's redraw this compound. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so we have excess of LAH. So the excess LAH will bring a second LAH. And the aldehyde will also react because I made an aldehyde. The aldehyde also react with LAH, will get reduced. So the LAH will reduce at the same time the aldehyde I just made. What happens? That O minus doesn't move, right? That O minus stays, right? Untouched because the one that reacted was the COO. So it comes now, it comes the H3O plus. So the H3O plus will protonate that one and also that one, right? Both of them will get protonated with acid, both of them. So I will have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 OH. Okay. 1, 2, 3, 4, 5. This one has OH and this one has OH. 1, 2, 3, 4, 5 OH, OH. These H2s, where are these H2s? Yeah, these H2s are here. Right? Yeah, that's it. That will be the mechanism for this reaction. You want to see the full mechanism or you want the highlight? That one was the highlight. That one was the highlight. And that one was the highlight. Okay. Let me see. A, a, a full view of the mechanism. Yeah, see the full mechanism for the lactone For some students that say like, oh, you always do the easy mechanisms, you never show the difficult mechanisms. This one is a difficult mechanism. So I'm showing you, it's the same thing. Okay, so professor, this mechanism seems more difficult than the monohydride on ketones or the, what was the other one? Or the LAH on aldehydes, right? Or vice versa, doesn't matter. Yes, it's easier. So this one looks more like a quiz question, and this one looks more like an exam question. Okay. With that, I'm telling you everything. So be ready for the quizzes for the other mechanisms, and for the exam, you might be ready for, for the ester or carboxylic acid mechanism. So, professor, is the carboxylic acid mechanism similar to this type of mechanism? Yeah, I mean, it is a little bit more complex. So for now, I will just leave it with ester. The carboxylic acid does undergo very similar, but it has an exception because it has the lithium as a transition, as an intermediate. So let's just keep the carboxylic acid for now. Let's just leave it as the mechanism of the ester. Okay? Because remember that here you guys can do ester or carboxylic acid. I show you the mechanism with the ester. I didn't show you the mechanism with the carboxylic acid. So are we gonna ever do it? No, not now, not yet. Okay. And here they're also showing you the mechanism with the ester only. They are not showing you the mechanism with the carboxylic acid. Okay. So if you're tired, it would be a good time for you to take a break. Okay. So and then uh, and then because we're going to start a new reaction, it's called the Grignard reagent or Grignard reaction. The next one is the Grignard reaction, right? So in the Grignard reaction, we have this particular compound is abbreviated as RMG MGX. Of course, that's not the Grignard reagent. It has an actual halogen, it has an alkyl or any carbon, any carbon group here, but magnesium is the central atom. So this is one type of compound that is known as organometallic compound. Organometallic compound means that it has a metal and also has some organic molecule. So this R is really the organic molecule. The magnesium is the metal. So we will see later on some other type of organometallic compounds. So for example, organolithium will be one. And then here we have the cuprate will be another one. Cuprate is somewhere here. Yeah, here's with copper, right? Copper. We have Grignard, we have organolithium. There are many more organometallic compounds. Some other courses, some other schools, they take an actual chapter on organometallic chemistry. It's a field of organic chemistry, but we will only see reaction of it. Okay, so the Grignard reaction. As you can see in this slide, right, the Grignard reagent reacts with many compounds. So here we react with aldehydes, right, acetaldehyde, no, sorry, formaldehyde, aldehydes, ketones, ester. Here is acyl halides, amides, another type of amide with carbon dioxide, with conjugated ketone, right? So two types of conjugated ketones depending on the catalyst, and it's a very strong nucleophile. It's a better base than nucleophile, but in this cases we use Grignard as a nucleophile. Okay, so Grignard reagents, how are the Grignard reagents synthesized? The Grignard reagents are synthesized by reacting the alkyl halide or aryl halide. It can be aromatic or it can be aliphatic. It doesn't really matter. So you react it with magnesium, and then you make immediately the Grignard reagent. So the magnesium basically gets oxidized, and then those electrons from the magnesium, you remember that magnesium belongs to the group 2A of the periodic table. 2A periodic table means that it has 2 electrons. Those 2 electrons go to the alkyl group. Okay, so I'll show you how that reaction happens. I mean, we don't need to know it, but let's say that you guys have, let's say, an ethyl chloride. We react it with magnesium. Magnesium has 2 electrons. Those 2 electrons get transferred to the carbon. Okay, so to the carbon, of course, the carbon dot CH2. So you form a carbon ion. No carbocation, now it's a carbon ion. And then the magnesium, of course, has +2 the Cl is -1, therefore these two combined, right? It will have a plus charge. Right? Plus 2 -1 is MgCl is plus. So this is really the Grignard reagent. So you see in the Grignard reagent, right, those two electrons from the magnesium get transferred to the carbon. This one breaks, the chlorine leaves, right? The chlorine leaves, and the magnesium donates one by one the electrons to the carbon. Why? Because this carbon, right, is deprotected, right? I mean, it's already plus because of the departure of the chlorine. So the magnesium will donate electrons. At the time that magnesium donates electrons, it will become Mg plus 2. The Mg plus 2 will attach or bind to the chloride, making the MgCl. So you guys have this particular reagent, which is, this is what we call the Grignard reagent. This one can be done with any carbon group. So for example, what if I have isopropyl chloride? Well, if you have isopropyl chloride, magnesium, you guys will get isopropyl Grignard. So you can write it like this, MgCl, but really what it means is minus, right, electrons, of course, and then MgCl. It's a carbon ion. So if you are making a, let's say, cyclohexane, cyclohexyl chloride, with Mg, what really this means is a minus there and MgCl. Okay, you see? It's a C minus. It's a very good base and also it's a very good nucleophile. Okay, Professor, you're only doing with chlorine. Can I also do it with bromine? Yeah, you can do it with bromine. I have, to be honest, I have only seen it with chlorine and bromine. Iodine, I don't know. To be honest, I don't know if iodine will be a good candidate. And I have not seen Grignard with iodine, maybe, but definitely with fluorine, no. So it can only be with chlorine or bromine. Those are the most common. Iodine, I don't know. To be honest, I don't know. I don't know if it's a Grignard, right? Halides. Okay. If you have a benzene ring, it also works. Right? If you put magnesium, the magnesium will bind. Right? The lone pair of electrons. Could be at the carbon. There is no CCR, right? There is no carbocation here anyway. So the electrons will be sitting right at the carbon that used to have the halogen. So that's how you guys have the Grignard reagent. Okay, great. So that's we don't need to know this mechanism, by the way. So it's only, I'm just showing you how it occurs. All right, so let's continue. So Grignard, Francois Grignard. So in 1912, he received the Nobel Prize because of this particular reaction. Okay, it was one of the first the pioneers in this particular organometallic chemistry. So this one is bromobenzene with magnesium. You get the Grignard, and here is the plus and the minus. So this Grignard reagent adds to any carbonyl compound, and then that's how you guys are going to be making different types of alcohol. You see, if you have a ketone, you make a tertiary alcohol. Remember that before we were saying that you can make primary or secondary alcohols. Remember here, primary, secondary. Some of you maybe were asking, like, what about the tertiary alcohols? Can I make tertiary alcohols? Yes, you can make tertiary alcohol with Grignard. This one is your tertiary alcohol. 1, 2, and 3. So it's 3 branches. That's how you make the Grignard reagent. First, you use a Grignard. Second, you use acid and water. Okay, so let's do it. This one with hands-on approach. That's the way how you guys know I prefer to do reactions. Okay, so how do they work? So this one is already messy. Okay, so how to use Grignard? So if I have let's say if I have cyclohexanone, okay, if I use Grignard, so let's say methyl Grignard, step 1, step 2 is acid. Okay, so what is going to happen is that the methyl will add to the carbon of the COO. CH3, the Grignard, whatever is next to the magnesium is what adds to the COO. And on the other side, you guys get the OH. Okay, that's all. That's all you guys have to write. Now the mechanism, how does that work? That mechanism we need to know, okay? The Grignard, remember that the Grignard, we showed that it was CH3 lone pair MGBr, right? Plus, right? That lone pair of electrons, of course, attacks the carbon because this carbon is delta plus. That's why the minus targets the nucleophile, targets the delta plus. And this one will break the octet. That's why it pushes the electrons to the oxygen. So the oxygen gets negatively charged and the methyl adds to the C double O. What happened with the MGBr? A spectator ion, so nothing on the side. And then you are adding in the second step the acid or water, and the O minus deprotonates it, right? Gets protonated. Yeah, that's it. That's the mechanism for the Grignard reaction. Do we need to know this Grignard mechanism? Yes, we need to know this mechanism. Okay, so that's really how it adds to a carbonyl. You are getting here a tertiary alcohol. You see tertiary alcohol. This carbon has 3 branches. What if I do it with an aldehyde? Yeah, you do it with an aldehyde. You will get a secondary alcohol. Okay, so let's use ethyl Grignard. Here, the carbon chain next to the magnesium is 2 carbons, right? 1 and 2. So those 2 carbons will get added to the C double O. The C double O will gain those 2 carbons. So my product would be H. The C double O will get converted into an OH. And these 2 carbons will be added to the other side. So what did I make? I make a secondary alcohol. So if you do Grignard on an aldehyde, you will obtain a secondary alcohol. If you do Grignard on a ketone, you will get a tertiary alcohol. How do I make primary alcohols? You have to use formaldehyde. Formaldehyde, if I use, let's say cyclohexol Grignard. Okay, cyclohexol Grignard, you guys will get uh, whatever is next to the magnesium, the whole group will be added, right? And the other side has the C double O. The C double O gets converted into an OH. And this is a primary alcohol. Okay, so now we know the additional way how to make primary alcohols. Primary alcohols, we do it with Grignard, any Grignard, and formaldehyde. Secondary alcohols with an aldehyde, and the Grignard. And the tertiary alcohol, you can make it from Grignard, right? Any Grignard, and the ketone. Okay, ketone for tertiary, aldehyde, any aldehyde for secondary, and formaldehyde for primary alcohols. Okay, right? So we need to know that mechanism. 43, I show you already one. Here is the overall reaction. Right? So here you have a reaction, you have a ketone, and you're making a tertiary alcohol. This one should show you the mechanism, right? I already showed you the mechanism, how to do it. That's the reaction for the Grignard. That's exactly the same molecule that I was using as here it's telling you, right? A ketone with a Grignard will give you a tertiary alcohol. An aldehyde with a Grignard will produce a secondary alcohol. Esters will also produce, right? It will also react with Grignard, and it will produce a tertiary alcohol as well. But that one will undergo 2 Grignard additions. Why? Because after the first Grignard addition, you will get a ketone. But ketones also react with Grignard. So 2 sequential Grignard additions will give you the tertiary alcohol. Okay, excess Grignard reagent will also give you a tertiary alcohol where the R group is attached twice. So the Grignard adds twice. Okay, so I'll give you an example. This is an example for this particular case. Let's use any ester. Dun, dun. Yeah. Methyl propanoate. I said I'm using excess ethyl Grignard. Okay, ethyl Grignard excess, it will add twice here. That's the COO. You will add twice. What twice? Twice methyl. Twice to the COO. Okay, so so you add twice. What happened with this or something? With this or something, that's a side product, CH3OH. That's right. This is this side chain. So that one gets eliminated. So it's a side product. So going back to this, right? So the double O, remember it becomes the OH, and you're adding this guy twice. So ethyl once, ethyl twice. So you are making a tertiary alcohol. So the Grignard is added twice, one here and one here. Mechanism for this, yeah, we can do the mechanism. I have no problem doing the mechanism. The first one is the ethyl Grignard. I'm going to abbreviate it with ethyl Grignard like this. Okay, ethyl Grignard, the ethyl with the lone pair of electrons. The lone pair of electrons will attack the COO. This one goes up. Now this one will come back down. This one is a leaving group though. So that's why it will get this, it will get lost. See, COO, I'll reform the COO. The ethyl, I just move the ethyl here. Now, since I have excess of Grignard, the Grignard will add again to the ketone that I just made. The ketone I just made will be attacked by the Grignard, and then I will add another ethyl here. And of course, the oxygen takes the electrons, right? Good. Oh, I lost here the CH3O, right? CH3O, it was lost as a side product. So here, when I add then the H3O plus the oxygen takes the hydrogen and this one returns. That's your product. All right. Tertiary alcohol. Tertiary alcohols used, all right, made from the ester. The ester gives you a tertiary alcohol. Okay, so ketones, tertiary alcohols. Aldehyde, secondary alcohol. Formaldehyde, primary alcohol, and esters, tertiary alcohols. Okay, so that would be the conclusion for the Grignard, right? The use of Grignard. That's the. So one of the disadvantages of Grignard, Grignard has some limitations. The Grignard, unfortunately, does not. Since it's a very, has a lot of electrons, right? Has concentrated electrons. The electrons will definitely interact with any acidic group. So you cannot use Grignard if you have you cannot use Grignard if you have an acidic group like OH, NH, SH, or carboxyl. They do not react because the H is present, so it cannot be cannot be made in the presence of those compounds. So what should I do then, Professor? If those groups are present, you have to protect them. You use a protecting group, and the protecting group will take care of it. Okay, so also you cannot do Grignard, let's say like you cannot do Grignard on ketones, aldehyde esters if in the same molecule you have these guys present. Why? Because these guys also react with the Grignard, right? Remember that the Grignard reacts with many compounds. So you have any of these compounds inside your molecule, of course the Grignard will be reacting with them. So make sure that your Grignard is reacting only with your target ketone, aldehyde, or ester, and then none of these groups are present, right? And also you cannot have any free OH, free NH, free SH or free carboxyl group. Okay, so for example, what am I trying to say is like, what happens if I have, let's say, right? So let's say that I want to do a Grignard. You say like, oh, I know that ketones can react with Grignard, but I have an OH here. What happens if I have methyl Grignard? You say, I want to make an alcohol out of this ketone. Yes, but you have an OH here. This reaction will not proceed. It will not adhere. What is the Grignard going to do? Well, the Grignard, remember, is a good base. It's also a nucleophile, but it's a better base. So it will deprotonate this H. It will deprotonate it. So the methyl Grignard will attack the H instead. So your product would be this. It's not going to react with the COO. The COO will be just sitting there waiting. What happened with the methyl? Well, the methyl will take the hydrogen. It will become CH4. It will add with the acid. So it's not going to react with the actual COO that you. Remember, any compound will always prefer to react as a base instead of a nucleophile. What about the other species? So let's say I have carboxylic acid and I have aldehyde. You say, oh, I want the aldehyde to react with my Grignard. No, the aldehyde is not going to react with the Grignard, unfortunately. The aldehyde is a electrophile. It will react first with the acid. This one is my acid. So it's an acid. So the Grignard will immediately react first with the acid. So your product would be COO. So your aldehyde will be laughing, I mean, because it's not going to do the reaction. What happened with this methyl? Well, the methyl gained the H, so it will become CH4. You lost it. You didn't do any addition. It will just be a carboxyl group. Who are those groups that are bad? OH, NH, SH, and carboxyl. Those groups are bad for Grignard. They will do a side reaction. Okay, so let's go back. Okay, using Grignard for synthesis. Yeah, so we're starting now the synthesis part, right? So how to use there is one more reaction, but now let's do the synthesis. How do I use Grignard in synthesis? So let's say like they tell me like I need you to synthesize this tertiary alcohol. So you have different alternatives, and then here it will show you, right? So you see here the tertiary alcohol. You have 3 branches as any tertiary alcohol. So the idea is to synthesize it. Remember that with using a Grignard, how you synthesize this alcohol? Well, one of these 3 branches has to be the Grignard. It can be methyl Grignard, ethyl Grignard, or phenol Grignard. This is called phenol. Phenol. I'll write it in a minute. Phenol Grignard. So here are your alternatives. So in this case, you are opting to use ethyl as the Grignard. So if ethyl is your Grignard, that means that the green portion will be your ketone. That's the ketone. This other alternative, this other approach, is using the methyl as a Grignard. That means that this blue side is going to be your ketone. That's why the ketone is right here. And in the red case, you guys have that the phenol is the Grignard. That means that your ketone will be right here. See? Ethyl Grignard, methyl Grignard, and phenol Grignard. They all take you to the same product. So there is no limitation. It's not like the SN2 reaction. Oh, the SN2 primary, right, is preferred over the secondary or tertiary. No, in Grignard doesn't exist anything like that. So in Grignard is reactive, and it will always give you the same product. Okay, so same thing. I'll stop, and then I'll give you a hands-on. Okay, an additional example. So let's say that you are having this particular tertiary alcohol. Okay, so here they tell you like make this tertiary alcohol. What are your options for this tertiary alcohol? Okay, my tertiary alcohol, so I can do, let's say I will use this as my Grignard. Looks like a man, right? All right, this is my Grignard. Then the second option, and my third option. This is my Grignard. I circle in one Grignard. In this option, I will use this as my Grignard. And in this third option, I will use this as my Grignard. Okay, so each of the branches can be used as an alternative for a Grignard. So that means that my Grignard will be methyl Grignard. If in this case is this, then my Grignard will be ethyl Grignard. Good. And in this last case, if this one was my option, I would be isopropyl Grignard. Plus what? What is left? It would be this chain would be left, right? So since this one left, right? So instead I have to make a ketone. What would be my ketone? Well, let's look at it. Ketone there. Okay? Right here. Ketone right there. No more OH, will be ketone there. Why? Because the Grignard is where the Grignard will attack. Right? Here. If this one is my Grignard, this one is gone. Now this one should be my ketone. Right? What is left? Here. So my ketone would be, that would be my ketone. Right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Why? Because the Grignard will attack right here. Okay. And in the last case, this is my Grignard. This is gone. Now I have to make the ketone with whatever is left. So that would be, this one is the carbonyl, the C-double-O carbon. So this is gone. Now the rest should be, this is my Grignard. 1, 2, 3, 4. 1, 2, 3, 4. And that's 1, 2, 3 carbonyl, 1, 2, 3 carbonyl. Right? Those are the options. So that's, you can do that with any tertiary. Professor, can I use the same approach to make a secondary alcohol? Absolutely, yes. You can use the same thing, of course. Let's say you tell me like, Professor, I want to make this alcohol. Can I make this alcohol from Grignard? Absolutely, yes. Remember that here you have an H. Okay, so if you have an H, then it limits your options for Grignard, but you can still use Grignard for this. It's an H, right? So which one will be my Grignard here? Okay, I want this one to be my Grignard. Okay, what about next one? Okay, now I want this one to be my Grignard. Remember, this one is your carbon, right? The carbon, the central carbon, this one. Professor, can I have an option in which I can use the H as a Grignard? No, 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 no. You cannot have this as a Grignard. This option is not available. You cannot have H as a Grignard. Okay, it has to be any carbon chain as a Grignard. So in this case, in a secondary carbon, right, in a secondary alcohol, you will have either Grignard here or Grignard here. What, Professor? What if I have a primary alcohol? Then you will have only one Grignard as an option. You wouldn't have two Grignards as an option. Okay, so in secondary you have two Grignards. In tertiary you have three Grignards as options. Okay, so here let's go back. This one is my Grignard. My Grignard is the one in circle. That's my Grignard. I replace the conjugated with a little circle in the middle. That's totally valid. And here will be the ethyl, right? Ethyl Grignard. Okay. If the benzene is gone, so I will have that ketone. So, well, in this case, it will be an aldehyde. H, right? HCOO, CH2, CH3. Down. What about here? Now here, this is gone. What's going to be left? HCOO, and then the benzene ring. That's it. Okay, so those could be the two options, how to synthesize this particular tertiary alcohol, right? This one, sorry, secondary alcohol in this case. Okay, so those are cases or examples how to make a Grignard, sorry, how to make a tertiary alcohol from, using Grignard reagents. Right, so let's continue now with the next one, next slide. We have protecting group. Remember that we were saying that OHs were a problem for Grignard, right? OHs was OHs, NHs, SHs. Well, since we are in the chapter of alcohols, there are some cases in which you want to protect your alcohol, right? The alcohol, I want the alcohol to be protected. So what should I do? Okay, if you want to protect the alcohol, then you will use a protecting group. Protecting groups are specific compounds, could be ions, could be molecules that they bind to your target functional group and then protect it. They protect it means that they are hiding it. They hide it, they let you do whatever you want to do with the rest of the molecule. And once you are done with that, you can deprotect it. In this case, for alcohols, the protecting group is trimethylsilyl ether, like TMS. We call it TMS. It's not the TMS from NMR. Remember, in NMR we have a standard internal standard, right, which was called TMS, but that TMS was the abbreviation of tetramethylsilane. In our case, is trimethylsilyl ether. Okay, so it would be TMSO. Yeah, you can call it TMSO, right? So tetramethylsilyl ether, right? So that would be your abbreviation for the protecting groups, right? TMSO. So TMSO is the protecting group for alcohol, and then it will protect the alcohol from anything, and then it will do the right. It will allow you to do any reaction, and then you can protect the alcohol, and then deprotect it with either acid or fluoride ions. Right? This is an example. This one is a clear example of how you can use it. For example, here I have bromide and I have OH, and use TMS chloride, right? Trimethylsilyl chloride, in using this tertiary amine as a base. Right? It protects it, converts the OH into OTMS. Then I make a Grignard. The Grignard is made with the BR. I make the Grignard, and then it will produce the Grignard. What happens if I don't protect the OH? If you make the Grignard in the presence of the OH, remember, OH hates Grignard. So it will react with it. So it will not let it be. So that's why you have to hide the OH while you finish your Grignard. And then once you are done with the Grignard reaction, then you can deprotect it. In the meantime, you cannot deprotect it. Okay, so that's the case. Okay, so basically, I'll just give you another example, right, of the use of alcohol. So let's say that you are having, right, you have this particular amine, and you have an OH, right? You have these two. So let's say that this you want to react it with methyl chloride in an SN2 reaction. You would say, like, what should I do? Okay, the methyl chloride, yes, I know that amine is a good nucleophile. The good nucleophile will selectively react in an SN2 reaction, right? But you observe that, yeah, it will attack, but your product, you have only a 60% or 65% yield of that reaction. What happened with the other 35%? The other 5%, the OH was the one that attacked the methyl. Why is that? Because OH is also a nucleophile. Even though it's a weak nucleophile, but it's also a nucleophile. It will compete with the amino group. Of course, is less than half. I mean, it's about half, right? It's half about the strength, but it will still, you don't want this 65-35, right? You want 100 here. You want a higher percentage. So what should you do? I have this compound. I need to react it with this compound, but I want only the amino to do this substitution. I don't want the OH to do the substitution. What should I do? Okay, so you want to do that, then have the amino, the OH, you will add the protecting group. You're going to protect it. TMS chloride in triethylamine. This one, what it's going to do is going to protect the OH, OTMS. Now, this OTMS is not a nucleophile anymore because the OH is hidden. So now what I will do? So now you can add the the methyl chloride, and now the amino will have the attack with no competitor. The competitor is hidden, is blocked. So now the amine is going to do the reaction with a higher percent yield. Okay, so what should I do next? Well, next, after you are done with your reaction, I don't think you guys want to see the product. But that's okay. NH, that's the product. You add it once, right? The methyl. The methyl was added, and then you deprotect it with CH3 or F minus. I think it was TBAF, I think. Tetrabutyl ammonium fluoride. TBAF, and then it deprotects it. And you get the OH. Okay, so that's the deprotecting. I can use that, or I can just say F minus, or I can say H3O plus. Okay, those three groups, and then you deprotect. You see, so you're overcoming an issue, a problem that you have for substitution. Two nucleophiles competing for the same substrate. So if these two are competing, giving you like an unnecessary side product or byproduct, then I want to cancel out this OH. So what should I do? Protect the OH, block the OH with the OTMS, and then do the reaction that you desire without the interference of the OH. And now after that, they protect the OH with TBAF, and then you get the OH free. And now that's your target compound. So Professor, the same way you have a protecting group for OH, do you also have a protecting group for amines? Yes. Do you have a protecting group for ketones? Yes. Do you have a protecting group for aldehydes? Yes. For carboxylic? Yes. You have a protecting group for every single functional group. And we will be learning them one by one as we move on, right, for our course. Okay, so this is another example. The example that we had in the slides was really that the BR OH, you had to protect it with TMS chloride in triethylamine. You had to protect the OH, OTMS, so you make the Grignard. The Grignard was made OTMS. It exists. What happens if you don't block it? If you don't block it and you make the Grignard directly, right? You make the Grignard directly before doing the protection, you will make the Grignard. Yeah, no problem. You will make the Grignard. But unfortunately, the Grignard is made in the presence of the OH. And OH is bad for Grignard. Since it's in the same molecule, what is going to happen is this one is going to disappear. You will produce this one, right? 1, 2, 3. 1, 2, 3. And this one will get deprotonated. Who deprotonates it? The same carbon deprotonates it, and will get O minus. Okay, so that's why this path wouldn't work. You have to protect it, and once you get the Grignard, you do the reaction. I think that they make it react with formaldehyde or something, but they do some more reactions, additional reactions after that. But that's the idea, is that you want to prevent the OH to be present because Grignard is bad, right? Does not exist or coexist with OH groups. Okay, next slides. Okay, that's the TBAF. You don't need to memorize the structure. You can just put F minus. Really, that's the active side. Conversion of alcohols, right? Alcohols can be converted to alkyl halide. That one we have done it already in Organic Chemistry 1, Chemistry 230. So you protonate it, and then it becomes a good living group, right? Alcohol, right? Remember that alcohol, to make a good living groups, you were using acid. The acid will make it a good living group, and then the bromide will attack it, getting a tertiary halide. Primary alcohols, they do the same thing, the same type of reaction. This one is an SN1 reaction, tertiary, because tertiary substrate, they prefer to do SN1 with carbocation. Primary alcohols, no. Primary alcohols get protonated, but then the bromide attacks in an SN2 style. That means synchronized, right? It leaves and attacks at the same time. Here, no. Here is in a two-step reaction. Leaves and then attacks. Two separate steps. That's the difference between SN1 and SN2. Primary alcohol, you can speed up this reaction. You use a catalyst with zinc chloride. Zinc chloride helps you to to lose the OH, right? Because this one is a primary substrate, so it's more difficult to do it. So this one is called the Lucas reaction, the Lucas test, to produce an alkyl halide. Okay? Good. Another conversion, how to convert alcohols to halides. We have done this reaction before, tosyl chloride. You can tosylate the alcohol, do with tosyl chloride, and then once you have the tosylate, you substitute. It's an SN2 reaction. We have done this reaction already. It will, remember, SN2 give you full inversion. So if this alcohol is chiral, then it will be reversed in the product after the NABR. Tosylation does not change. What changes the stereochemistry is the nucleophile. The nucleophile is the one that does the SN2. This reaction is not SN2. This is the SN2. So the only reversal, right, will be after the NABR. So the NABR will change it. So OH, you can do another alternative, right? If you don't want to go through this, so you guys can use, you can use SOCl2, thionyl chloride. Let me write it. Thionyl chloride, right? SOCl2, thionyl chloride, or PBr3, phosphorus tribromide. Anybody says those long names? No. Everybody will always say SOCl2 or PBr3. So we always say like, okay, alcohol with SOCl2. Okay, so that means that the OH gets converted into Cl. The OH gets converted into bromide. Mechanisms for this? No, we don't need to know mechanism for this. Okay, so at least those are the good news for this particular part of the of the uh, of the slides. Oxidizing agents. So we are going to oxidize the alcohol. So remember that earlier I was telling you that the oxidation path, right? Aldehydes, and carboxylic acid. Well, there is also an oxidation path, so you can oxidize, right? The oxidation path and the reduction path. So we can also oxidize alcohols. Alcohol get oxidized. You have two oxidizing reagents, chromic acid, okay? It can be sodium chromate, sodium dichromate, or chromic acid alone. So you can see that NaCr2O7, or chromic acid, H2Cr04, or sodium chromate, Na2Cr04. Right? I'll show you. I'll write the structure for each. Or you can have a partial oxidation with PCC. PCC stands for pyridinium chlorochromate. It's like a poison oxidizer, right? So it's a poison oxidant. Pyridinium is a poison, so chlorochromate is a strong oxidant. But in the presence of pyridinium, that oxidizing power gets decreased. So that's why it's less oxidizing than chromic acid. Okay? Primary alcohol with PCC will give you aldehyde. Primary alcohol with chromic acid, it will go all the way to carboxylic acid. Secondary alcohol with PCC or chromic acid will give you ketone, and tertiary alcohol, they do not oxidize. Okay, so those are the, here is the, a summary of the oxidation. This is the summary of the, I mean, I'll give you an example for oxidation, but this one is a good summary chart for the reaction we studied in this particular chapter. All those reactions. This is the IR to remind you what is an alcohol. This is the alcohol side. This is CHSP3, yes. And that's all. Here is the, no, we don't have anything else. NMR, that's the alcohol. Remember, alcohol NMRs, they will always are exchangeable hydrogens. So you won't see like a well-defined peak for OHs. That's an OH. Where else is an OH? Maybe this is the OH. We don't have the structure, unfortunately. Let me see. No, they don't give you the structure for this. So we're not gonna really determine it. I mean, we could. I mean, this one is a is an aromatic. I think what it is. Yeah. This one should be, I mean, if you can let me guess. Pause it right now, work it, pause it, and then I'll show you the structure for the first one. Okay, the structure for the first one should be this. That's the structure for the first one. That's on your own, okay? The structure for the next one. Oh, let me see. I know what it is. Okay, it's this one. And I don't know the answer, to be honest. I don't think I'm trying to show off. I'm not showing off. I'm just giving you, I'm trying to guess what it is. This one, let me see. This one is a triplet. 1, 2, 3, 4, 5, 6. 6, that means that it has a CH3. Oh, okay, I know. I know what it is. Propanol. Yeah. This one right here is this one. This one is the alcohol. This one is this one. And this CH3 is this one. Here, these 5 H's are the aromatic, right? This one will be the most de-shielded. The most de-shielded will be this one. Then this one should be this one. And of course, the alcohol is the 1H. This one, yeah. So that one is the, right? The tall 9H's. Tall 9H's. That's the terbutyl. That's the alcohol. And the para substitution, right? Para substitution on a benzene ring. 1 each. That's it. Okay, so let's go back to the oxidation part, right? The oxidation, the oxidizing agents. Example of oxidation of alcohols, oxidation of alcohols. So you guys will have different alcohols. Let's say you have a, yeah, primary alcohol, propanol. What happens with propanol is a primary alcohol. Primary alcohols in the presence of PCC and dichloromethane. The chloromethane is just the solvent, okay? So in the case of PCC and the chloromethane, it gives you a partial oxidation. That means that the primary alcohol will be oxidized only to aldehyde. Partial oxidation with PCC. What happens if I have the same, but I use sodium dichromate? I think they use acid. Let me see. Do they use acid? I think so, right? Yeah, sulfuric acid and water. Sulfuric acid and water. It's oxidizing. It oxidizes all the way to carboxylic acid. Okay? All the way to carboxylic acid. So PCC, partial oxidation to aldehyde. Sodium dichromate, it goes all the way to carboxylic acid. That's what happens to a primary alcohol because it's primary. In primary, you have the option. You can do partial oxidation and full oxidation. Secondary, no. Secondary, you do only one type of oxidation. So from secondary to ketone. Okay, so another option to, instead of sodium dichromate is sodium chromate. That's sodium chromate, Na2CrO4, also in sulfuric acid and water. Or you can just say H2CrO4. You can also use just that's chromic acid. Or this, or this, or this. Right? These three things are equivalent. That's primary alcohol. What happens if I use secondary alcohol? Let's say cyclohexanol. What happens if I use PCC in dichloromethane? Well, the secondary alcohols, they have no option. They can only get they only get oxidized to ketone. What happens if I use chromic acid? Same thing, ketone only. Professor, why is that? Why secondary oxidized with the same, there is no partial and total, and in primary there is partial and total. Why? The reason is because the carbon here has two hydrogens. The carbon here only has one hydrogen. So if you lose one hydrogen, you have the partial oxidation. If you lose the two hydrogens, you have the total oxidation. Okay? What happens in a secondary alcohol? You only have one hydrogen available. So that means that if you lose this hydrogen with PCC, it will take you to ketone. Dichromic acid. Technically, chromic acid should take two hydrogens, but this carbon doesn't have two hydrogens, only has one. So even if it tries to oxidize, it won't do it. So that's why you have the same product for both reagents, because the secondary alcohol only has one oxidable, let's call it like that. One hydrogen can be oxidized. So what happens in tertiary alcohols then? Tertiary alcohol, they do not oxidize. Why? Because tertiary alcohols, the carbons don't have any hydrogen. This is terbutanol. This carbon has no hydrogen to lose. So can this one get oxidized? No, it cannot get oxidized. Why? Because it has no hydrogen to lose. You need a hydrogen to get oxidized, right? Remember the rule before? You lose hydrogen bonds or you gain oxygen bonds. In this case, you need to lose hydrogen bonds, but you don't have any hydrogen bond to lose. So even if you use PCC excess, even if you use chromic acid excess, it will give you no reaction. It will not oxidize if it's a tertiary alcohol. Why? Because there is no hydrogen to lose. Okay, so that's the important thing. That's something that we need to remember. All right, so now the last part is going to be synthesis. Let's do some synthesis, and then that will be the end of our lecture. Synthesis for this chapter. So let's do a couple, or at least 3 or 4 synthesis reactions involving alcohol synthesis. Okay, so let's say, okay, so let's say they tell me synthesize using, I want you to synthesize this alcohol. Okay, they tell me go from here to here. We're on chapter 12, right? Remember, chapter 12. So you have to use the reaction of chapter 12. Of course, in some cases, you might have to bring back the reaction from chapter 8, 9, 10, 11, right? But in the majority, the synthesis will be focused on the chapter that we are really studying, okay? So what is this? This is an alcohol. How do I make alcohols? Well, alcohols, from this chapter, I can make it from different ways. So I can do a reduction of aldehydes, reduction of carboxylic acids, right? I can do it from Grignard. I can do a substitution, right? Substitution, SN1 or SN2. What else? That's it, right? So those are the ways that we learned today. Now you have to see what are the ways how you make an alcohol. That's what we learned. Okay, it's a primary alcohol. So now my starting material. What is the starting material for for this alcohol? Aldehyde. Do I have an aldehyde? No. Do I have a carboxylic acid? No. Can I make a Grignard from this? Yes, I can make a Grignard from this. Can I do a substitution SN1 or SN2 on this? No. Because remember, aromatic compounds, they don't undergo substitution. But I have this one. This one is my escape. I can do Grignard. Perfect. Let's do a Grignard. So let's use the same strategy that we had before, right? HH, right? Remember that we had to select, right? So what would be my Grignard? My only Grignard will have to be this guy. I cannot have H's as Grignard. Okay, so let's make a Grignard. Can I make a Grignard from that benzene ring? Yes. I mix it with magnesium. And I have magnesium green, phenol. Oh, I was gonna say the spelling, right? Phenol. That's the group, phenol. P-H-E-N-Y-L. Phenol Grignard. Okay, phenol Grignard. And then what should that be? Okay, so this one is my Grignard. Then what is left? HH. And that HH is gonna be a formaldehyde because it's a primary alcohol. That's step 1. Step 2 will be H3O plus, right? Because it always needs H3O plus. And after that, it will give me the product. Ta-da! That's the synthesis involving alcohols. Okay. Another one, let's see. Involving alcohols. This one is fun. Okay. Accomplish the synthesis. You have this OH, and this aldehyde gets converted into carboxylic acid. How can you do that? So definitely there is no change here. Okay, nothing here. 1, 2, 3, 1, 2, 3. There is no change, right, in the length. This one gets changed from aldehyde to carboxylic acid. How can I do that? I can do that by oxidation. If I oxidize aldehydes, I can go to carboxylic acid. What should you use? Oh, well, you use sodium dichromate, right? Sodium dichromate or chromic acid. Can I use sodium dichromate directly? No. Why? Because if you use sodium dichromate, it will oxidize, yes, true. But unfortunately, it will also oxidize the alcohol. The alcohol will get oxidized immediately also to carboxylic acid. I don't want that. So what should I do then? I want to protect, I want to hide that OH so I can work on the aldehyde. Okay, let's do it. Okay, so I have the compound. Let's protect it. How do you protect it? With TMS chloride in triethylamine. It will protect the alcohol, TMSO. After that, what should I do? Oxidize it. Oxidize it with sodium chromic acid. Chromic acid or sodium dichromate, right? It will oxidize it. And after that, I deprotect it with fluoride, TBAF. Good. That's it. It deprotects and then it gives me the OH. You said that, professor, but the dichromic acid is acid. Acid is also a deprotecting group. Yes. It is true, but it's not on this slide, but is acid in heat. Okay, acid and heat is the deprotection. You have to deprotect it because you make an ester. Esters are, to hydrolyze ester, you need heat, a lot of heat. This one, dichromic acid, no. This one, dichromic acid, can be done at room temperature. So even though you add here dichromic acid, the acid is not gonna deprotect it. Why? Because you need heat for that. So acid and heat. TBAF, no, doesn't need a heat. So that's why it's more convenient to use fluoride to deprotect it. Okay, that's the difference between acid and heat, and then acid, in this case, dichromic acid. Okay, that's another synthesis. See, synthesis, we're evolving the synthesis. It's not just plain memorization, and then they get also a little bit shorter, right? Shorter in the sense like only three steps. Okay, I'm gonna be doing 2 more examples for synthesis, and then if you think that you had enough, I mean, you can definitely close this video. But if not, I have additional problems for you guys to practice. Okay. Okay. So the next synthesis, what are we doing in the next synthesis? Let's make a secondary alcohol. Let me think. Okay. So let's just give me a second. All right, so I came up with these last 2 syntheses. Here in this particular synthesis problem, they're asking us to make this conversion. You can see they are both alcohols. This one is a secondary alcohol. This is tertiary alcohol. All right, so remember, the main goal of synthesis is always to investigate or how to make the product. First, your target is to analyze the product. Your product in this case is a tertiary alcohol. How can we make tertiary alcohols in this chapter? In this chapter, we can make tertiary alcohols by reacting either esters with Grignard or ketones with Grignard. right? So that's how you can make tertiary alcohols. Esters with Grignard, excess Grignard, or ketones with Grignard. So that's the whole point. So can I make a ketone from that? Okay, well, I have to analyze. So this tertiary alcohol, either my Grignard could be here, or could be here, right? Those are my potential Grignards, right? So, and then, but I have to pay attention to something. What does this product share in common with my starting material? My starting material is right here. 1, 2, 3, 4. So that means that most likely my Grignard was this guy, right? The one on top. That's the one that was added. Okay, that one. Because this is exactly the same. 1, 2, 3, 4, and then OH. So that is the extra. Okay, it is necessarily, I mean, not always, but I mean, that's what I can see, right? If I compare the starting point, the starting material, and the final product. So that means that this one was my Grignard. So if that's my Grignard, that means a methyl Grignard. Followed by H3O plus. That means that what used to be my ketone? Well, the ketone used to be, if this one is gone, that's the ketone. Now, can I make this ketone from this compound? Yes, you can make that ketone from this compound. How? There's an oxidation reaction called PCC in dichloromethane, and you can get to that conversion. Professor, can I use sodium dichromate in sulfuric acid and water? Yes, you can do either one. Or this or this. So both of them work. That's a synthesis that you can do. So it's also a conversion of alcohols. That's very easy. Okay. Another synthesis that I prepared for you guys. This alkene converted to a carboxylic acid. Well, in this chapter, we learned how to make carboxylic acids, right? Oxidation of what? Of alcohols. Yes. Oxidation of alcohols. So what type of alcohol? Primary alcohol. What else? What else do we know about carboxylic acid? How can you make carboxylic acid from this, from oil or one? It was from alkynes, right? Remember, guys, alkynes. You have alkyne and you do ozonolysis on alkynes, you can get carboxylic acids. But the disadvantage of this reaction is that you cleave the molecule, you cut it. So your starting material loses carbons, at least one, right? In this case, I have 1, 2, 3, 1, 2, 3. I'm not losing any carbon, so I cannot use this reaction. So what should I do? I have to use a reaction that is the oxidation of a primary alcohol in the presence of sodium dichromate, right? Sodium dichromate, sulfuric acid, and water. It will oxidize it to carboxylic acid. Now, that's what it comes from here. Sodium dichromate, sulfuric acid, and water. So what would be the starting material for this previous step, right? If you go backwards, 1, 2, 3, alcohol. Now, can I make this primary alcohol from this alkene? Yes, that is chapter 8. There is an addition of alkene anti-Markovnikov. That reaction is called hydroboration. BH3THF followed by hydrogen peroxide, sodium hydroxide. Okay, so that's why we need chapter 8, 9, 10, and 7. We will need it all the way. Why? Because it is kind of like a bridge. Those are the basic reactions of organic chemistry. And we will need it, right? We will need them to process, part of the synthesis, exercises that we will have in this course. Okay, so we had few examples, right? So 4 synthesis problems. So hopefully, you get a taste. That's the idea. Definitely it's impossible for me to do every single synthesis possibility in a lecture. I don't want to make the lecture longer than what already is. Okay, so but that's the type of a strategy. Always investigate your final product. See, put on the side what are the options. How can I make this tertiary alcohol? That's how I do. For example, here, secondary alcohol. How can I make a secondary alcohol? Here, those are my options. And then once you guys have that, that short list, you guys will analyze your starting material. What starting material is more accessible to my options? And based on that, you guys will do your step. Okay, so in some cases, you have to go back to the foundation or go one, but in some other cases, you don't have to. Okay, so that's my recommendation. Please let me know you guys have any questions about this chapter 12 on alcohols and phenols. We covered only alcohols. Phenols is really not something that we're going to be doing for this course. It's only except the acid-base properties. Okay, so let me know you have any question, and then take care. I'll see you guys soon.